Right, so hello and welcome everyone to week 9 of interactive live sessions for the course on fundamentals of convective heat transfer. This course is being offered by NPTEL and it's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I am a PhD scholar at IIT Madras and like every other week, we shall be solving a few problems together related to the lectures of week 9, which continued our discussion on natural convection, which we started on week 8. So, without further ado, let's jump into the questions. Um, here. So, this is question number 1 of today's session, which is asking us which of the following heat flow situations pertains to free or natural convection. Is it option A, air conditioning installations and nuclear reactors? Option B, flow of water inside the condenser tubes? Option C, cooling of internal combustion engine? Or option D, cooling of billets in atmosphere? So there are four different kind of heat flow situations given, mostly pertaining to engineering applications, and you have to figure out which one pertains to free or natural convection and not forced convection on the contrary. So once you figure out the correct solution, you can either type in the chat box or you can unmute and answer. It's a very simple question to start off today's session. Which of the following heat flow situations pertains to free or natural convection? Is it option A, air conditioning installations and nuclear reactors? Option B, flow of water inside the condenser tubes? Option C, cooling of internal combustion engine? Or option D, cooling of billets in atmosphere? Okay, we have one response in favor of option D, saying that it's cooling of billets. Okay, we got one more in favor of option D. Now let's have a look at the correct solution. The correct solution is indeed option D, cooling of billets in the atmosphere. So all these other three, these are related to forced convection. There is some, you know, intended flow being driven through either fans or by uh, compressors or pumps to maintain a required amount of flow so that there is a forced convection. On the other hand, this option D, cooling of billets in the atmosphere, in which simply pieces of metal, pieces of hot metal, are left in the atmosphere and then they cool by natural convection currents. So this one is the correct solution. Okay. So this was a very simple first question to start off. Then we will move on to question number 2, which is asking us that from integral solution of natural convection. This is something that we learned in the initial few lectures of week 9. The ratio of average Nusselt number to the local Nusselt number at y equal to h is what? 4 by 3, 3 by 4, 2 by 3, or 3 by 2. There are four options given below. Try to figure out the correct one, and you can type it in the chat box or you can unmute and answer as well. So this is the question. Uh, so there is a vertical plate like this, and there is a natural convection current being set up, and this is y, this is x. So now the question is, what is the ratio of average Nusselt number? So the average Nusselt number at h and the local Nusselt number at h. But the ratio between these two is what? So this could be the height h. So the ratio of the average Nusselt number throughout the entire zone and the local Nusselt number exactly at h. What is the ratio between them? Is it option A 4 by 3, option B 3 by 4, option C 2 by 3, or option D 3 by 2? Okay, so let's have a look at the solution. So unless the integral solution is performed, there is no other simple way of finding this out. So you have to know how to do that. And the correct answer is 4 by 3. So the average Nusselt number at y equal to h, this becomes 4 by 3 times of the local Nusselt number at y by h. So that's why option A would be the correct answer. Now there is one thing, since Nusselt number profiles with whichever axial direction you are going against is usually very high at the initial. Uh, you know, uh, I wrote S here. S could be both X or Y, depending on whichever orientation you take. And here's Nusselt number on the uh, vertical axis. So it's the Nusselt number is usually very high where the boundary layer just begins. So over there the boundary layer thickness is very low, and with the streamwise direction the boundary layer will also grow. And due to that growth, there is usually a decay of Nusselt number. So no matter what happens, the local Nusselt number at any point and the average of whatever was there earlier would always be greater than the local one. So this is one uh, pattern that most cases of boundary layers follow, be it forced convection or natural convection. You get my point, right? So any local position I pick, the average up until that location would always be higher than the exact value at that location. This is true for Nusselt number in case of heat transfer. Uh, for hydrodynamic boundary layers also, the what is that? So the shear stress, the average shear stress would be uh, always higher than the local shear stress at any location. Okay. So any questions regarding this? Alright, if there are no questions, we will keep moving on. We'll move on to question number 3. Now, this is an interesting one. So, it is asking us that match the similar cases with respect to natural convection over an inclined plate. So, there are four options given here. So, four cases rather. So, hot side facing downward. So, it's something like this. So, the hot surface is this one. There will be a boundary layer growth. G would act this way and the flow would go this way, upwards. Or it could be hot side facing upward. So in this case, so this is case 1, this is case 2. Then we have cold side facing upward. I'll take a different color here. So cold side facing upward is this. So now the boundary layer would start from the top and go towards the bottom. G is still acting this way. This is case number 3, and we have cold side facing downward. This is case 4. So velocities in both these cases go towards the downward direction. So you have to pick out what are the similar cases among these 1, 2, 3, and 4. So which are physically similar, that the physics process is the same in which cases. So option A is 1 and 4 and 2 and 3 are similar. Option B says 1 and 2 and 3 and 4 are similar. And option C says 1, 3 and 2, 4 are similar. So 1, 3 and 2, 4 are similar. And option D says none of the above. So there are no similarity among any of these cases. That's what option D is saying. So you have to pick out the correct option among these four. Okay, we have one response in favor of option C, saying 1, 3 and 2, 4 are similar. Let's see what others have to say. We have one response in favor of option C, saying that 1, 3 and 2, 4 are similar. Let's see if we can get some more answers out there. You can either type it in the chat box or you can unmute and answer as well. Okay, so let's have a look at the solution. The solution is indeed option C, 1, 3 and 2, 4. So I'll go back to the figure over here. So as you can see, these two figures, 1 and 3, for the first case, the flow is moving upward and towards the plate. Get the point, right? So there is a upward motion due to the buoyancy change, and that's why it's moving toward the so this can be divided into two components. One is along the streamwise direction and the other direction is toward the plate. So the growth of the boundary layer would be restricted. It would be a thinner boundary layer. The same thing happens for this case also, for case 3, where buoyancy change drives the flow downward, and that can again be split into two components, one along the streamwise direction and another component towards the plate. Now if we go to, that's why option 1 and option 3 are similar. And if we move to option 2, case 2 and case 4, we can see that here the upward motion can be split into two components, one along the streamwise direction and the other one away from the plate. So the boundary layer thickness grows. And same thing happens for case 4 as well. So that's why 1, 3 and 2, 4 are physically similar. The physics of the problems are exactly the same. So if I take y-axis in the uh, direction oriented to the movement of the boundary layer, or not movement of the boundary layer, but towards the direction of growth of the boundary layer, then mathematically also this would give rise to same forms of equations. So that's why option 2 and option C, that says case 1 and case 3 are similar and case 2 and case 4 are similar, is the correct answer. Am I making sense? Are things clear? Okay, so if there are no questions, we will move on. Move on to question number 4. Now, this is asking that between the two cases undergoing natural convection, which one would have a higher Nusselt number? Hot side facing downward. So, what I mean is, okay, so use a different color plate. Uh, so, let's focus on hot sides only. So we already saw that hot side facing downward and cold side facing upward means the same thing. And what option 2 says that hot side facing upward or cold side facing downward are the same thing. So let's consider only the hot sides upward and downward. So what I mean is there are these two cases where the hot side faces downwards. There is a cool air over here, and the second case where there is a uh, hot plate facing upward. Okay, sorry, I'll draw this straight way. So this is a hot plate and there is an ambient fluid upwards. So T-wall and T-wall in both cases, uh, the T-wall is greater than infinity, meaning it's a hot plate. So which one among these two, case 1 and case 2, would give rise to a higher Nusselt number? Would have a more efficient heat transfer? Which case would have it? What do you think? Option 1 or option 2? Okay, so we have one response saying it's option 2. Let's see what others have to say. Option 2 means that hot side is facing upward or cold side is facing downward. Okay, another response in favor of option 2. Okay, let's have a look at the solution. And indeed, option 2 is the correct one. So, uh, we saw that the Nusselt number for this first case would be something like 0.27 into Ra to the power 1/4, which is the Rayleigh number. And for the other case, where hot side faces upward or cold side faces downward, in that case, Rayleigh number is 0.54 into Rayleigh number to the power 1.1 by 4. So you can see that this is almost double that for the same given the same Rayleigh numbers. And physics wise, what happens is that let's say I have a hot plate like this, so the fluid over here would immediately move up after getting heated up, and colder fluids from the ambient would rush in to compensate for the vacuum created, and this would create these convection currents like this. On the other case where I have a hot plate facing downward, the fluid over here, this gets heated up and this has to cross over and move this way. So there is a lot more resistance facing it, and there would be cold air again coming in from the bottom to compensate for that. But then again, uh, this movement of this hot air away from the plate is not something that is very much fluid mechanically feasible. So that's why the Nusselt number for the second case is much higher than the first case. So this is case 1 and this is case 2. Any questions regarding this? Okay. Okay. So we will move on. We'll move along to question number 4 now. So question number 4 is asking that for natural convection over a sphere, where is the maximum value of H? Theta equal to 0 degree, 180 degree, 45 degree or 90 degree. So what I mean is simply this. I have a hot sphere which is at a higher temperature than the ambient. There is a convection current being set up this way, and I'm measuring theta this way. So I call this y and this is x. I'm measuring theta from y. So this is this is theta. So this is theta equal to 0 degree would be here. Theta equal to 45 degree somewhere here. Theta equal to 90 degree over here, and theta equal to 180 degree. Sorry, I couldn't draw this. And theta equal to 180 degree over here. So among these four locations, location uh, A, B, this is C, and this is D. Among these four locations, where would be the value of H maximum? Okay, we have one response in favor of 0 or A, And another one also telling it's 1. Okay, so by 1, I'll assume that we mean option A. Let's see what others have to say. We got two responses. So I'll give you a hint here. The main determinant over here is the thickness of the boundary layer. Okay, we have another response in favor of option A. Alright, so let's have a look at the solution. Solution is indeed option A. All of you are correct. So I'll go back to my figure here and see. So for option A, the boundary layer thickness over here is the minimum, and for this one, it's the maximum, and these two are intermediate cases. So this delta being less would mean the value of H being higher, because the temperature gradient would be higher. So this would mean dou T, dou R would be high, and this in turn would mean that H would be higher, because as we know that HA delta T is same as K into dou T dou R in this case. Get my point, right? So this being high would also mean that H would be high. So that's why option A is the correct answer over here. Okay. Any questions on this? Okay. So if there are no questions, we will keep moving on. We move on to question number 6 of today's session. Now this is a numerical type question. So this is asking us to consider a hot horizontal cylinder. So cylinder like so, of length 1 meter and diameter 0.2 meter, is placed in a cold liquid. So you have to calculate the rate of heat loss. The data given is, let PR for, okay, not air, it's a liquid. Let PR of that air is equal to 0.559, and the thermal conductivity K is equal to 0.025 watt per meter Kelvin. And you can take the Rayleigh number for the particular flow condition as Rayleigh number equal to 10 to the power 6. So all these pieces of data are given. The Nusselt number is also, this is Churchill's formula, Churchill and Chu. Churchill and Chu's formula for uh, natural convection over cylinders placed in fluids. So using this formula, you have to find out what the rate of heat transfer is. So try solving for this, and you can type your answer in the chat box, or you can unmute and say as well. And if you are facing any difficulties while solving this problem, please don't hesitate to talk about it. We will try to figure it out together. I will anyway be solving it after some time, but it's important that you try to do this by yourself, because these are the type of questions we can expect in the NSEM, or not NSEM, the final exam for this course. So how would you try to solve a problem like this? What would be the first step?
To calculate the Nusselt number first.
Right. So if we try to sorry, uh, if we try to calculate the Nusselt number first, we have zero point 0.6 plus 0.387 into Rayleigh number to the power 1 by 6. So our Rayleigh number is 10 to the power 6 to the power 1 by 6. This would simply become 10. And on the denominator, we have 1 plus 0.559 divided by Prandtl number, which is also 0.559. So these pieces of data was taken so that our calculation is much easier. So to the power 9 by 16 and this whole thing to the power 8 by 27 squared. So this would finally give us Nusselt number equal to zero point 0.6 plus 3.87 divided by, so this becomes 1, right? These two cancel out. 2 to the power 8 by 27. Okay, this is a weird number. But anyway, try to can anyone calculate this and tell me what Nusselt number finally comes out to be? 76.33, is it? 76.33. I'll just check one side. I want to make sure that we are doing this correctly. So 2 to the power 8 by 27. This is 1.227. So 3.87 divided by 1.227, and this thing plus zero point 0.6, and then this has to be squared. Hey, I'm getting a much lower value of 14 point something. Are you sure about that 76.33? 3.75? That's even lower. Okay, this part was correct, right? 1 plus 1 to the power 9 by 16 is still 1. So it becomes 2 to the power 8 by 27. 2 to the power 8 by 27. This is 1.227. So in the next step, this becomes zero point 0.6 plus 3.87 divided by 1.23, let's say, and this thing squared. So 3.87 divided by 1.23 is 3.146, and if we add zero point 0.6 to it, this becomes 3.74. 3.746 squared. If we square this, then it becomes 14 point something. Yeah, 14.035. That's what someone told in the chat box, I guess. Yeah, 14 point something. So we will take this to be 14 itself. For our ease of doing things. Then, finally, what do we need? Finally, we need the rate of heat loss. So rate of heat loss is H into A into delta T. So we know delta T, we know A, we have to find out what H is. So H d by K is equal to Nusselt number, which is 14. So from here we can find out h to be k, which is 0.025 divided by d. D is zero point 0.2 into the Nusselt number, which is 14. Right. So this becomes, let's see, I lift this, so it becomes 200. I'll lift this one as well. So it's 25 by 200 into 14. So 25 by 200 is 8. 4, 7, h equal to 7 by 4. And if we use that value over here, so q equal to 7 by 4, then the total area is pi dl, right? So it's pi into d into l, which is 1, and delta t is 50. So finally this becomes 7 into, okay, zero point 0.2 into 5 is 10, right? So 2 into 5, 10, yeah. So 70 divided by 4 into pi, which is 54.9, so roughly 55 watts. So this is the correct answer. Any questions, anyone? So the process is clear, right? Right? How do we tackle problems like this? Yeah, okay. Give me a second, I'll be back. Okay, so this was question number 6 of today's session, and we'll move on to question number 7 now, which is asking us that by integral solution of natural convection over a flat plate, velocity profile is given by so. So this is a finding. Now you have to find the location of maximum velocity. Where is it? Very simple question. Try to find out where it is. The location of maximum velocity. Okay, so by we have a velocity profile that is given. We just have to find out the location of maximum velocity. It's simply a math problem of finding the maxima of a given function. So where will be the maxima for this function? Okay, we have one response saying that it's 1/3 of delta. Okay, uh, so let's try solving for this. We already have everything that we need. So the velocity profile is given. So V I can write as V naught into x by delta into 1 minus x by delta squared. So I'll extend this out by performing the square root, the squaring, not the square root. 2 into x by delta plus x by delta whole squared. And if I multiply this x by delta with each term, I'll get v naught into x by delta. Sorry, this won't be there. X by delta minus 2 x by delta squared plus x by delta cubed, right? Okay. So now if we have to find out the maxima, then the derivative of that function has to be 0, right? So this has to be 0. This gives us that dou v dou x is equal to v naught into 1 by delta minus 2 into 2x by delta plus 3 into x squared by delta cubed, and this is delta squared. Sorry. So this, now this has to be 0. Now this is a simple, uh, you know, quadratic equation. So we will try to solve for this now. We will send this v naught to that side, making it 0, and then multiply delta cube with each term. So that would finally give us 3x squared plus 4x, delta cube we are multiplying, so there will be a 4 delta x, and this is minus not plus. 4 delta into x and plus delta cubed by delta. So delta squared is equal to 0. We can split this middle term into 3x squared minus 3 delta x minus of delta x plus delta squared is equal to 0. We can factorize this. So 3x minus delta into x minus delta equal to 0. So there are two solutions of delta, that is solutions of x, that is delta by 3 from the first one and equal to delta for the second one. And if we now actually physically try to see how this velocity profile might look like, so it's something like this, right? So, and this being delta. So at delta, it can't be the maximum velocity, right? So that's where the velocity boundary layer is. That's why the velocity of the fluid becomes equal to the velocity of the quiescent fluid in the ambient, which is at rest. So this cannot be the maximum. This one should be the maximum, and this is at a distance of delta by 3, x equal to delta by 3. So this is the solution for this. So the location of maximum velocity would be x equal to delta by 3. Simple stuff. I hope it is clear. Any questions on this? Okay. If not, we will move on to the next question. Okay, there are no more questions. That was the last one. So thank you everyone for joining and participating. We will meet again next week at this time, and we'll solve some more problems together. So thank you.
Thank you, sir.